Hi. See, it's a good thing that I'm able to give you the answers to the quiz questions on the application of Newton's laws of motion. This quiz was tough, is tough, and is therefore going to be very important for the exam. So let me try to, as clearly as possible, explain each answer. Question 1. There's a 60 kilogram person who wishes to push a 180 kilogram mass across a level floor. The coefficient of static friction between the person's shoes and the floor is 0.7. What is the maximum coefficient of static friction between the box and the floor, such that the person can push horizontally on the box and cause it to start moving? Two important things here that you notice: that there is friction between the person's shoes and the floor, and also there is friction between the box and the floor. Now that's important. That's a person there trying to push. Friction always opposes motion, and since the person is trying to push the box in that direction, friction between the box and the floor will be in the opposite direction. At the same time, when the person tries to push on the box, there is a chance of him slipping backwards, which means he tends to move backwards, and therefore the friction between his shoes and the floor is in the opposite direction. So now you see that the friction is actually opposite to each other. And according to this problem, we do not want the person to move, we do want the box to move. Now that's the important point. Friction is given by the product of the coefficient of friction times the normal reaction. Now therefore the friction on the man is going to be mu times the normal reaction on the man, which is going to be his weight, because his weight is acting straight up, right? So that's 60 times 9.8. So the friction between the shoes of the man and the floor is 412 newtons. Remember that is the normal reaction, which is the same as his weight. Now the friction between the box and the floor, using the same formula, is mu times 180 times 9.8. But why am I saying that that should be equal to 412? Because only if that's equal to the other frictional force can you ever make the box move. Otherwise, it's impossible to make the box move. So the friction on the box can be a maximum of 412. You see, maximum of 412. If it's less than 412, surely the box moves. If it's more than 412, then the man moves backwards. Okay. So since we do want the box to move, when you just make that little calculation from here, you get the mu as 0.233. Second question. A car drives over a hilltop that has a radius of curvature 120 meters at the top of the hill. At what speed would the car be traveling when its tires just barely lose contact with the road when the car is at the top of the hill? So the car is right at the top of the hill, and you know that the two forces acting there are, one, the weight acting vertically down, which is the centripetal force. Now, which is mv squared by r? That's the centripetal force. And we do not want this car to entirely lose contact, which means the centripetal force must be equal to its weight. The mass cancels out, and you're asked to find the speed, which is square root r times g. The radius is 120 meter, g is 9.8, and you get the answer as 34.3 meter per second. 34.3 meter per second. In this question, a 4 kilogram block rests between the floor and a 3 kilogram block as shown. The 3 kilogram block is tied to a wall by a horizontal rope. If the coefficient of static friction is 0.8 between each pair of surfaces, that means between these two and between these two, between each it's 0.8. What force must be applied horizontally to the 4 kilogram block to make it move? Already from the question it's understood that there is friction between the 3 and the 4 kilogram boxes, and also between the 4 kilogram box and the floor. And since friction opposes motion, and you're trying to pull it this way, friction here is going to be opposite. And again here, since the box is trying to move away from underneath, again friction is going to be opposite. So that's why I've shown friction in both cases to be against motion there. And what's friction? Friction is given by mu times Fn. I call them F1 and F2. So F1 is mu times Fn. What's Fn here? Fn is the normal reaction, and it's going to be the total weight of the two boxes. Because at this point you have weight of 7 kilograms acting, so you're going to say 0.8 times 7 times 9.8. This is 54.88 Newton. But when you look at this point, the normal reaction here is only the weight of the 3 kilogram. Only the weight of the 3 kilogram. That's going to be the normal reaction here. Okay, so that's 3 times 9.8, which gives you 23.5. So the total applied force must be the sum of the two, which gives 78.4 Newton. That's clearly understandable. In this fourth question, a box is sliding down an incline tilted at an angle of 16 degrees above the horizontal. The box is sliding down in the incline at a speed of 1.90 meter per second, which means that's the initial velocity. The coefficient of kinetic friction between the box and the incline is 0.420. How far does the box slide down the incline before coming to rest? Which means the final velocity is 0. So you know the initial velocity, you know the final velocity. You're asked to find how far it slides, which is delta x. And in order to do that, you need to know the acceleration of the box. In fact, it is a deceleration here because it's slowing down. So you need to calculate the A. And the only formula to calculate A, or acceleration, is net force divided by the mass. Net force divided by the mass. So let me complete the diagram. That's the box sliding down. Now that is the weight. Weight always acts vertically downward, and that's mg. And the frictional force is against the motion. Since the box is tending to slip down, the frictional force is up the plane. The angle here is 16 degrees, and that's the normal reaction Fn. Now the weight mg can be resolved into two components, and you will see that this component is going to be mg cos theta, because this angle is theta as well, which is 16 degrees. And so this becomes the adjacent side, and that's mg cos theta. So you see that mg cos theta should be equal to Fn. These two are equal and opposite because the net force along the y-axis is 0. And again, friction is given by mu times Fn, which is mu mg cos theta, because Fn is equal to mg cos theta, which is mg cos 16, and that gives you 0.993 mg. And since we are looking for acceleration, acceleration is the net force divided by the mass, which is what we got already divided by the mass. The masses cancel out, and that gives you 9.73 meter per second squared. Once you have the acceleration, you know the initial velocity is 1.90 meter per second. The acceleration which we got just now, it's supposed to be negative because friction is an opposing force. Looking for delta x, and the final velocity is 0. The equation to be used is Vf squared is equal to V naught squared plus 2a delta x. Rearrange, make delta x the subject and substitute. And when you do that, you get the answer as there's a negative there and another negative in the denominator, and on calculation you get it. In question 4, a box is sliding down an incline tilted at an angle 16 degrees above the horizontal, and it has a speed of 1.90 meter per second. The coefficient of kinetic friction between the box and the incline is 0.420. How far does the box slide down the incline before coming to rest? Alright, the box is sliding down, and from this problem you understand that it is slowing down. Now why is it slowing down? It's because of friction. Now is there any other force that is helping it to move? Yes, there is the component of the gravitational force, but it looks like that is not as big as the frictional force. That's the reason why it's slowing down. Okay, we will start with a diagram. That's the box. The weight acts vertically down. Frictional force is against the motion. The angle is 16 degrees. The normal force is Fn. And the weight can be resolved into two components. You get mg cos theta and mg sin theta. So now you see that the frictional force is against the box sliding down, while mg sin theta is helping it to come down. And we got to find, well, technically this diagram is not correct because the frictional force had to be bigger. Okay, that's why it's slowing down. So that's what we're going to find. Okay, frictional force is given by mu times Fn. Mu is given, but Fn is mg cos theta. Fn is mg cos theta. So when you substitute, get cos, okay. Actually, you get 0.40 mg. That's okay. Now, the net force is the friction minus mg sin theta. Friction acting up minus mg sin theta. And when you take sine 16, you get 0.28. So it's 0.28. There should be an m there. Okay. So the difference is 0.12 mg. And acceleration is the net force divided by mass. So the mass cancels out. And it's only 0.12 times g, which is 1.18 meter per second squared. The initial velocity is 1.90, the final is 0, and we are asked to find the displacement. We just got the acceleration as 1.18, and I should have paid more attention to significant figures, because just now I noticed that there's supposed to be 3 significant figures. Well, it's too late, but we'll get close to the right answer. Vf squared is v naught squared plus 2a delta x. Rearrange, make delta x the subject, get Vf squared minus v naught squared by 2a, which is minus 1.90 squared by 2 times 1.18, which gives 1.53 meter. So the answer is close to A, which is 1.44 meter. Okay. In question number 5, what is the terminal velocity of a 6 kilogram mass falling with a drag force with a magnitude that depends on speed, as F drag is 30 times V? So you know that terminal velocity happens when the drag force is exactly equal to the weight of the object. Now that's the crucial point here. Here the drag force is given as 30 times the velocity, and that should be equal to the weight. That's when an object has terminal velocity. That is, the net force acting on it is 0, which means the force upwards, which is the drag force, becomes equal to the weight acting downwards. And therefore from there, mass is 6 kilograms, g is 9.80 divided by 30, and 1.96 meter per second is the terminal velocity. Number 6, a ball is tied to the end of a cable of negligible mass. The ball is spun in a circle with a radius 2 meter, making 0.7 revolutions per second. What is the centripetal acceleration of the ball? So the cable itself, you need not consider its mass because it has a negligible mass. And the first thing here is, what is given as revolutions per second needs to be changed into meter per second. You know that in one revolution, the total displacement, the total distance is equal to the circumference. And the circumference of a circle is 2 pi multiplied by its radius, 2 pi r. So that is, if that's the distance in one revolution, then the distance in 0.7 revolutions would be that multiplied by 0.7. Okay, so velocity is along the tangent, and the centripetal acceleration is given by v squared by r. And that's why I was saying that you need to find out the velocity, because what's given is not the velocity. And 0.7 revolutions per second is 0.7 times the circumference, which is 2 pi times the radius. So once you get that velocity, square it, because it's velocity squared. So square both quantities and divide by the radius. And when you substitute all the numbers, you're going to get 38.7 meter per second squared. Remember that this will become r squared, and one of the squared terms will get cancelled with the radius, and this will become 4 times pi squared. So keep that in mind when you calculate. Number 7, an airplane is flying with a constant speed of 300 meters per second along a horizontal circle with a radius of 15,000 meters. If the lift force on the wings is perpendicular to the wings, at what angle relative to the horizontal should the wings be banked? Now, since it's making a horizontal circle, we need not consider the gravitational force, because gravity only affects an object that moves along the y-axis, and this is a horizontal circle. Therefore, gravity need not be considered. And since it's making a circle, the force that keeps it going around in a circle is the centripetal force. And we also know that the angle of banking is given by tan theta is equal to v squared by rg. Velocity is 300, radius is 15,000, g is 9.8. Therefore, the angle of banking is, when you take the arctan of that, 0.6122, and you get 31.5 degrees. So we use the same formula for banking of an airplane as we use for finding the banking at a curve in a road. Number 8, a 600 kilogram car is going around a curve with a radius of 120 meters, that is banked at an angle of 20 degrees with a speed of 24.5 meters per second. What is the minimum coefficient of static friction required for the car not to skid? So when you read this problem, you understand that the amount of banking is not enough to keep the car going around that curve. So you also need friction, and we are asked to find the coefficient of static friction. So let's break this down into two parts. We do know that the required force is the centripetal force, which is mv squared by r. That's what is required. That's what is necessary to make the car go around the curve. Oh, let's calculate that. That gives you 3001 Newton, and just to draw this diagram, that is the normal force. That's the component of the normal force, or those are the two components, Fn sine theta, which provides the centripetal force, and Fn cos theta is equal to mg. Okay, we know that this is Fn cos theta, and that should be exactly equal to the weight. So Fn cos theta equal to mg. We can use that to calculate Fn. So you get it as 600 times 9.8 divided by cos 20 degrees. And now you take, okay, so that's 6257, and therefore now you know that the banking provides Fn sine theta, which is going to be 6257 sine 20. So banking provides us with 2140 newtons, which is not enough. Look at this. Actually, you need 3001 newtons for the car to go around the curve, but you only get 2140 out of the banking. Therefore, the remaining force must come from friction. Therefore, the frictional force is the difference between the two. Which is 861 newtons, and you know that friction is mu times Fn. So now mu is friction divided by the normal force, which is 861 divided by 6257, and that gives us 0.13. Well, close to 0.12. In the ninth question, a car travels around 200-meter radius flat curve at 40 meters per second at a constant speed. What's the minimum static coefficient of friction which allows it to travel at the speed without sliding? Now notice that this is a flat curve. That means there is no banking, which means the required centripetal force is entirely due to friction. And friction is given by mu Fn. In this case, it's mu mg. Why? Because if it's a level road, then the entire weight mg becomes the normal reaction Fn. Okay. So the whole centripetal force is provided by friction, which is mu Fn, but Fn is equal to mg, so that's mu mg. Calculate mu, v squared by rg, which is 40 squared by the radius is 200 times 9.8, gives us 0.81. 0.81, which is close to 0.815. Okay, so that's the answer. In number 10, the magnitude of the drag force on a 20-kilogram object is proportional to its speed. The object has a terminal velocity 80 meters per second. What is the magnitude of the drag force on the object when it is falling with a speed 30 meters per second? Now, because we're given that the terminal velocity is 80 meters per second, and we do know that when it attains the terminal velocity, its weight is exactly equal to the drag force. Its weight is equal to the drag force. So at 80 meters per second, the drag force is equal to the weight. But the drag force is given as being proportional to its speed, so it's a constant multiplied by its speed or velocity. Okay, so that's how you write a proportionality as an equal. Multiply with a constant times the velocity. The mass is 20, g is 9.8. We do not know the constant, so we'll leave it as k, and the velocity is 80. That's the terminal velocity. So now from that you can find k, which is the constant of proportionality, which has this unit. And how do you get that unit? Is just by putting the unit of Newton, second, just F by velocity. That's Newton divided by meter per second, which is Newton second per meter. Okay, now we can find the drag force at 30 meters per second. It's the same formula. F drag is constant by times velocity. We already got the constant, and multiply by 30 to get 73.5 Newton. What is the terminal velocity of an 80-kilogram mass object in falling with a drag force with a magnitude that depends on speed, as F drag is equal to 12 times the velocity plus 4 times the velocity squared? Don't worry about the units of k there. We know that that's a unit from the previous problem. This is again to do with terminal velocity, and you're asked to find the terminal velocity of an 80-kilogram mass falling with a drag force which depends on this. Now, when does it get terminal velocity? When the drag force is equal to its weight. And what's the drag force given as? It's given as 4 times v squared plus 12v. I just rearranged it. I just put 4v squared plus 12v is equal to, that's the mass times g. On multiplication, you get 784. Rearrange it, and you get a quadratic equation. Minus 784 is equal to 0 there. When you solve the quadratic equation, which I'm not showing here, you can solve it using a calculator on the exam. That's not a problem if you know how to do it. When you solve it, you get the velocity as 12.6 meter per second. 12.6 meter per second. In number 12, a child stands on a playground merry-go-round a distance of 1.30 meter from the rotation axis. The coefficient of static friction between the child's shoes and the surface of the merry-go-round is 0.6. Assuming the acceleration of gravity is 9.81 meter per second squared, what is the maximum constant angular speed of the merry-go-round for which the child will not start to slide? Okay, this is again circular motion, and in circular motion we know that the centripetal force must be given or must be provided by something. In this case, that's provided by friction. It's very clear that it is the static friction between the child's shoes and the merry-go-round that provides the centripetal force, and centripetal force is mv squared by r, so that's equal to the friction. What's the formula for friction? Friction is mu times Fn. And this time we know Fn is mg. Should be mu times Fn. So okay, I had forgotten to write mu there. Now there is mu mg. Which gives us velocity is, okay, let me correct that. Velocity square root of mu rg. There should be a mu there, which I have to include, and that's what you find here, mu times the radius times g, which gives the velocity as 2.77, and then angular speed is linear speed by radius. So linear speed divided by the radius gives you the angular speed, which is 2.13 radian per second. 14. A 2 kilogram ball is moving with a constant speed of 5 meter per second in a horizontal circle whose radius is 50 centimeter. What's the magnitude of the net force on the ball? It's a horizontal circle. Gravity has nothing to do with it. Therefore, the only force here is the centripetal force given by mv squared by r, which is the mass 2 times phi squared divided by 0.5, because centimeter has to be changed into meter, and you get 100 newtons. That is the net force acting in this case.